First, let's do a little bit of a recap, a little bit of a recall. Given that differential equation that you were working on before, what we did in previous videos is we first went through a null-Klein analysis. I'm not going to repeat that whole thing, that's on a previous video. But then the next thing we did is we found straight line solutions, also known as Eigen Solutions. And the way we found them is if you algebraically manipulate dy dt over dx dt, you get dy dx. And from our thinking, from the fact that the lines, these straight lines, these Eigen Solutions pass through the origin, the slope, the derivative of those lines had to be just y over x. So we took dy dt over dx dt, and then we algebraically worked on that thing until we got to y equals negative 2x and y equals negative x. And so the idea was, let's leverage those Eigen Solutions so that we can find all the solutions. And I'm emphasizing that because we're going to use another leveraging today in this video. I hope you'll see it. But the cool thing is, look, if you can find solutions on those lines, you can find all the solutions. Isn't that awesome? And so the way we did it was start with one line at a time. I guess I did y equals negative x first. So dx dt is equal to negative x. Because look, y is equal to negative x. So dx dt is equal to y, which is negative x. And we're able to separate, integrate, and solve. Likewise, dy dt is equal to, well, if x is equal to negative y, hey, if y equals negative x, then x equals negative y. And so x equals negative y, and then this simplifies into just negative y. Ha! Look at that. They're both negative coefficient, and so we separate, integrate, and we get this. Then remember the deal with if the coefficient over here was c, and if y equals negative x, then the coefficient over here would have to be negative c, because, look, x is c e to the negative t. Do you see c e to the negative t? So y is the opposite of that. Huh, that's awesome. And then we leverage the other one. I did it here in green. If the straight line solution is negative 2x, well, if y equals negative 2x, separate, integrate, you get x equals, and I just use k this time as my constant, k e to the negative 2t. And then remember, y equals negative 2x, and so we were able to simplify this, since that was negative 2x minus 3y, y equals negative 2x. And look again, we got that coefficient of negative 2. Separate and integrate. And then likewise, if x is k e to the negative 2t, do you see x right there? K e to the negative 2t? And so it's got to be negative 2 times that, since y equals negative 2 times x. And then the cool thing was you can just put it all together. Take your solution from x up here, your solution from x down here, put them together. Take your solution from y up here, take your solution for y down here, put them together, and we've solved the differential equation. That is, we have x as a function of t, y as a function of t. Now, if you go on to p-plane and play around with that, you can click x as a function of t, y as a function of t, you can see those things. If you look at my video, I made a Desmos graph to show that those solutions actually make sense. Hey, I want to share with you another thing that we like to do in math to represent these solutions, and that is to write it as a matrix instead of, let me get there, there you go, instead of the way we had it before. Here's the matrix solution that you just saw. Here's how you read this. X is equal to c e to the negative t times 1. Where did you get the 1? Hang on. X equals c e to the negative t times 1. X equals k e to the negative 2t times 1. Where'd you get the 1? Hang on. And so if you read this kind of the top line, you get what the solution for x is. I hope you can see it from what we had before. And if you read the bottom line, y of t is c e to the negative 2t times negative 1. So it would be negative c e to the negative t. Where'd you get the negative 1? Hold on. And then y equals k e to the negative 2t times negative 2. Where'd you get the negative 2? Hold on. And so here's a way that we can express that same solution in matrix form. And here's what we do. Now the way it started is pretend that this one negative 1 wasn't there. That's a little one, let's see, it's a 2-row by 1-column matrix. So it's a 2-by-1 matrix, or a column matrix, or a column vector, we might even call it. That column vector is known as the eigenvector. And the eigenvector shows the relationship of that eigensolution. Remember the eigensolution of y equals negative x? So if x equals 1, y would have to equal negative 1. And then likewise over here, this came from the eigensolution, the straight line solution, y equals 2x. So if x equals 1, y would have to equal negative 2. We could put anything we want in those eigenvectors as long as we preserve the relationship on those straight lines that we were using. So you could put 2, negative 2. You could put 4, negative 8. As long as y equals negative x and y equals negative 2 times x, you're going to be fine. But it's common to go with the most simple versions, in this case 1 to negative 1, 1 and negative 2. All right, so now you have some more terminology here. The eigenvalues are those exponents, the negative 1 and the negative 2. The eigenvectors are those associated vectors that are associated with those straight line solutions, or eigensolutions. All right, now you should have read a little document and have some sense of the eigenvalue first method. I'm going to talk through it in the context of an example, actually the same example, so you can see that it does produce the same result, just with a different method. But along the way, I hope to help you see why it works the way it works. All right. Don't worry, I got you here. Here's how it works. I don't like how crooked that is, so just hang on a minute. I'm going to make that just a little bit better. All right, there you go. All right, here's how it works. So from the document that you read, dx dt equals y, dx dt equals y, or 0x plus y. dy dt equals negative 2x minus 3, negative 2x minus 3y. So here's dx dt, here's dy dt. What we found out over here previously is that dx dt is going to equal negative x. It's going to equal negative 1 times x. It's going to equal that eigenvalue times x. dy dt is also going to equal that eigenvalue times y. So dx dt is that eigenvalue times x, dy dt is that eigenvalue times y. Now, you have to get out of your mind that this, oh, by the way, this is the Greek letter lambda. Lambda is the letter we use for this eigenvalue in this context. So lambda times x, lambda times y. Lambda can have more than one value. In fact, it better. Lambda better be negative 1, remember the first eigensolution, and lambda better be negative 2, remember the second eigensolution. So what we're going to do is start there. dx dt equals lambda x, dy dt equals lambda y, because that's how it works out. But now we're going to start there. Instead of starting with straight line solutions, we're going to start here assuming straight line solutions. And we're going to go look for them. Now from the document that you saw, I hope you were able to track the matrix notation for this. It looked like this. So subtract lambda x from both sides. So I subtracted lambda x from both sides. Subtract lambda y from both sides. So I did that here. Did some algebra there. I hope you can track that from the document. But then express this system of equations as a matrix. Notice, coefficient, 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 coefficient. So that first matrix is known as the coefficient matrix. Those coefficients get multiplied by the variables x, y. Now, if you've never done a little linear algebra before, here's a little linear algebra for you. To multiply this 2 by 2 matrix by this 2 by 1 matrix, it goes like this. This times this, which you see right here, plus this, this times this, which you see right here. This times this, which you see right here, plus this times this, which you see right here. So you multiply, 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 multiply. So it's just a way to organize this system of not differential equations anymore, but this system, it's a way to organize this system in using matrices, and then equals the constants equals 0, 0. So the coefficient matrix gets multiplied by the variable matrix equals the constant matrix. Now what you saw in the document is, if we have straight line solutions, we're going to leverage the idea, now listen to that, like we leveraged straight line solutions over here, we're going to leverage an idea here of dependency. Now, two lines are dependent if they're parallel. So we're going to leverage that, and two lines are dependent if they're parallel, and if they're dependent, then their slopes, that thing that you saw in the document, all comes out to be 0. And so the determinant here, this 2 by 2 determinant, needs to be 0 in the case of dependency. So multiply minus multiply. 0 minus lambda times -3 minus lambda minus multiply. So this matrix here, this determinant I should say, as now we're thinking about it as a determinant, can be evaluated by this cross product minus this cross product. A little more linear algebra there for you about how do you evaluate a 2 by 2 determinant. So multiply across minus multiply across, you get this result. And that result has to be 0. So I hope you can see that 0 minus lambda is just negative lambda. Minus a minus, so it's going to be a +2. If I distribute that negative lambda, it's going to be +3 lambda minus a minus plus a lambda squared plus 2 is equal to 0. Or more conventionally, if we put it in decreasing order, lambda squared plus 3 lambda plus 2 is equal to 0. Now keep in mind, let's not lose sight of what we're going for here. We're looking for those eigenvalues. We're looking for the -1 and the -2 that we got first from our straight lines over here. Now over here, we're not going to find the straight lines first, we're going to find those eigenvalues first. The way we do it is we express our linear system here with the eigenvalues in there. From what the development on that page, you saw 0 minus lambda goes here, -3 minus lambda goes here, the -2, the 1. Do the determinant thing, cross product minus cross product equals 0, algebra, 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 and you're welcome. For this first case, this thing factors into lambda plus 2, lambda plus 1, which means lambda equals -2 and lambda equals -1. As we should not be surprised that that's exactly what happens. There's those eigenvalues. So the same eigenvalues that came from our straight line solution process over here are now coming from this eigenvalue first process over here. Cross product, set equal to 0, do the algebra. Now I hope you see in general, if you are doing this cross product determinant thing, you're always going to end up with a quadratic. And if you always end up with a quadratic, think about all the things that could happen. When you have a quadratic, that quadratic can intersect the horizontal axis twice, as it does here, -2 and -1. A quadratic can intersect a horizontal axis just once, as it does in this, as I'm just demonstrating here. Or a quadratic can theoretically not intersect the axis. So you could get 2 values for lambda, you could get 1 value for lambda. It's a repeated 0, we called it back in algebra. We could get a repeated 0, or we could get no eigenvalues. In fact, what happens here is you get imaginary eigenvalues. Now, what we're going to do for now is we're going to focus on looking for situations where we get real number eigenvalues so we can get solutions. In fact, will you practice writing your solutions in matrix form, please? I hope you can see now where that's going to come from. C e to the negative. Why is it -t? Because it's -t. k e to the negative 2t. Why is it negative 2t? Because there it is. And then because of our relationship on those straight line solutions, y equals negative x, y equals negative 2x, we can get the associated eigenvectors. So just a quick example there to make a connection. We'll do another example in the next video to hopefully bring it all together, but I wanted to just pause there for now and set up for where we're going. Yeah, real eigenvalues for now, but we will explore what happens in a phase plane when you have either one or none imaginary eigenvalues.